Hello. Now we will do the Ohm's law. In Ohm's law, we will make the relationship between the voltage across two ends of a conductor and the current generated in the conductor. And we will also learn about the concept of resistance in case of conductor. Okay. So this is a conductor we are having, and it's a cylindrical conductor like a wire. Its cross-section area we are assuming it to be uniform throughout, and the length of this conductor is L. This conductor is having two ends. One of the end is A and the second end is B. These two ends of the conductor is connected with a battery of fixed voltage, DC battery it is, fixed voltage B. Okay. So when we connect this battery with this conductor, obviously we know there will be voltage difference applied across this conductor. So because of the connection of this battery across the conductor, the voltage difference across the conductor, which is VA minus VB, will be equals to V. So potential difference will be applied across this conductor. And because of this potential difference applied across the conductor, there will be electric field which will be generated within this conductor. And as you can see, this conductor is uniform. Its cross-section area is uniform as well as its length is uniform. We can fairly assume that electric field generated within this conductor will be uniform throughout. So based upon that, we can say that V by L, voltage across the conductor divided by length of the conductor, which is equals to E. This is our first equation. From this equation, we can calculate how much electric field is being generated across this conductor. And because of this electric field, the conductors inside this conductor, which is the electron, free electron inside the conductor, they will start moving. And as we already know, the electron will be moving opposite to the direction of this electric field. So electron will start moving opposite to the direction of this electric field. And because of this movement of electron, the current will be generated across this conductor. This current which is being generated across this conductor will be taking it in terms of J, which is the current density. So because of the electric field, this current density will be generated across this conductor. Okay. Now we already know that there is a relationship between this current density and the electric field applied. The current density is equals to sigma times of E. The current density generated within this conductor is equals to sigma times of E, where this sigma is conductivity. Conductivity of the conductor. We already know this conductivity depends upon the internal properties of this conductor, meaning what kind of material it is. So once you select the material, the conductivity of that material is constant if the material is uniform throughout. So J is equals to sigma times of E. What we will do, we'll replace the values of J and E from the given equation. We already know that value of J is equals to I by A. The current density is equals to current divided by cross-section area. So from equation 1 and equation 3, if we put the values of E and J in equation 2, what we will get? We will get I by A is equals to sigma into V by L. This sigma, which is the conductivity of the conductor, this sigma I can also write it as 1 upon rho. Sigma is the conductivity and rho is the resistivity. Resistivity of the material, obviously. It is reverse to the conductivity. From conductivity, we get that how easy it will be for the electrons to move, and from resistivity, we get the resistance applied across the electrons so that they will not be able to move easily. So if we replace all these values, we'll be getting I by A is equals to 1 upon rho V by L. Or we can say we'll be getting V is equals to rho L upon A times of I. So the voltage is proportional to current. That's what we get. From here we are getting that voltage is proportional to current. So if we are having a conductor of uniform cross-section area, and if we apply voltage across that conductor, that voltage across the conductor will lead to the current inside the conductor. So the voltage applied across the conductor will be proportional to the current generated in the conductor. Okay, and that proportionality constant, if you see that proportionality constant which we are getting here, that proportionality constant is defined as the resistance of this conductor. So we say V is coming out to be proportional to I. So this proportionality constant we introduce as R. We define proportionality constant as R, where this R is defined as the resistance of conductor. So if we compare these two equations if you compare, we will be getting R is equals to rho L upon A. So if you see this equation, this is the relationship between the resistance and the resistivity. So you see this resistivity, it's the internal property. It is the internal property of the material. Basically, it depends what kind of material you are using. And if you see this L by A, it is dimensional property. So once you choose the material, the internal property is fixed. Then you think about the dimension, and once you get the dimension, you get L by A. So this resistance of the material, it depends upon the internal property as well as the dimensional property. If you change the material, the resistance will change. If you change the dimension, resistance will change. So this is how we define the resistance as a property of a conductor, which is related to which gives the relationship between the voltage applied across the conductor and the current generated across the conductor. So this is your Ohm's law. One thing we should always remember, that Ohm's law is only valid. Ohm's law only valid for conductors. It's only valid only for the conductors. We don't apply the Ohm's law for insulators, or in case in future you will study semiconductors. We don't use Ohm's law. So the Ohm's law is only applicable when we are dealing with conductors. Okay, and this is the formula for resistance which we are getting. This is the formula for resistance which we are getting. For this formula to apply, we have to have the uniform cross-section area of that conductor. If we'll be having a non-uniform cross-section area of the conductor, we'll not be able to utilize this formula, because while deriving this formula, we have assumed the uniform cross-section area of the conductor. So there are some conditions. This formula only valid for uniform cross-section area, which is A, only valid. So this is one of the formula one has to memorize, and this is one of the formula one has to memorize. This is always valid if it is a conductor. V is equals to IR, and the resistance we can get from this formula if the cross-section area of the conductor is uniform. Okay, so I hope you understood this. Thank you.